Assalamu alaikum jami'an. So today my presentation is going to be about phaco-dynamics, which is a topic not favored by many ophthalmologists. Phacoemulsification, as we all know, was started by Professor Charles Kelman, 1965, when he basically thought of the ultrasound power to fragment the crystalline lens while he was sitting on the dentist chair. In 1967, he performed his first phacoemulsification procedure on a human eye. From there, Dr. Barry Sabol used the term phaco-dynamics to describe the physics of closed system phacoemulsification surgery as a safe, efficient way to remove the cataract through small incision. So in my presentation today, we're going to talk about that closed system that is going to provide the proper phaco-dynamics for the best result after phacoemulsification. And in this presentation, we'll talk about two components of the phaco-dynamics, the ultrasound energy and the fluidics. For the ultrasound energy, which is the basic concept of the phacoemulsification, the ultrasonic oscillation of the tip, we will be mentioning a few subtitles of the direction and the timing and the different types of it, and then we will touch on the fluidics. So the ultrasonic energy that was first produced or introduced was using the longitudinal waves, meaning the movement of the tip that is going to come from in, out, and out, in. But then it was discovered that this movement, or what is called the jackhammer movement, utilizes half only of the energy, and the other half of the energy is wasted as it is not encountering a nuclear part to emulsify. And from there, the development of the lateral movement as well of the tip, which is the elliptical, and then finally the evolvement of the torsional ultrasound. In the torsional ultrasound, the movement is like shaving the material, and hence introducing the repulsion of the nuclear material, and it has less frequency and hence less complications and energy consumption within the eye. This ultrasonic waves are transferred by a phaco tip or a phaco needle, and the needle have evolved from a straight tip to a curved tip, and the curves have different degrees. All are in the favor of holding the piece and directing this ultrasound power directly to the nuclear part instead of wasting it into the eye. The power generation through that phaco needle movement is mechanical. And this power, the total power, is a combination of two factors: the frequency of the needle movement and the stroke length. The stroke length, which is the distance where the needle tip is moving back and forward, is about 2 to 6 mils, about 1.5 to 4 in many of the machines. And the longer the stroke length or this distance moving gives you more heat and greater cavitation forces. The power setting of the machine reflects the stroke length. So if you're setting your power to 50, 60, 100, then this is reflected on the stroke length. And of course, the surgeon can alter the stroke length or the power of the machine, the amplitude, in order to decrease the energy or the heat exerted. The frequency, on the other hand, counts the speed of this needle movement. So the movement is about 28,000 to 45,000 cycles per second, and this is the efficient amount of frequency that will help emulsifying the nucleus. Less than this is insufficient. More than that is dangerous to the eye. So we have touched a bit on the mechanical part of the ultrasound that talks about the longitudinal, torsional, and the circular or lateral phaco. But then there is another factor that emulsifies or helps in emulsification of the nucleus, and that is the cavitation effect. The cavitation effect is created energy that is released when microbubbles implode. Meaningly, with the movement of the phaco tip, there are high and low pressure zones created by the forward and backward movement of the tip. And then the compression of those microbubbles when the backward movement of the tip creates, they compress those microbubbles until they implode. And this implosion creates energy or creates more power that causes another factor that helps with the emulsification of the lens. Another thing that helps with emulsification is the coupling forces, the forces you use against the pressure against the nucleus, the second instrument, and other things that you utilize trying to help with the mechanically with the emulsification. So here we have touched on the direction, talking about the longitudinal and other forms of the movement of the tip of the needle to deliver the energy. Now we are going to touch on the timing or the mode of the energy. So we have three basic modes: the continuous, the pulse, and the burst mode. To understand more, it's very simple. So in the first mode, which is the continuous mode, as you can see, when you preset your phaco machine, for example, to 50, then as long as you are pressing the phaco pedal, you are going upwards the power until you reach the maximum preset phaco power you have already preset in the machine. And this is called continuous mode. This is linear continuous mode, as you can see here. The second mode I will talk about is the pulse mode. In this pulse mode, again, as you are pressing the foot pedal, your energy increases up to the preset level you have designed, but there is an off period in between your phaco pulses. And the benefit of the off and on periods that we're having there between the pulses is to decrease the energy spent in the eye. This almost reduces the energy by half, so it is 50% less energy wasted in the eye if you use the pulse mode. In the burst mode, the preset phaco power does not change, it's not linear, does not increase while you are increasing the, your foot pedal, your pressure on the foot pedal, but at the same time, the off period is getting less. So once you continue pressing to the maximum of the foot pedal, you will reach almost continuous phaco, but because of the off time is getting shorter and shorter between the pulses. Each one of them has an advantage, has a disadvantage in hand applications, but just to give you an example of how can we modify these alternate modes and powers in order to have less trauma to the eye, I'll give you an example. For me, my phaco technique is phaco chop in most of the cases. So basically, I skip the, this step of sculpting, but if those are using it, you can basically change the fixed mode, which means that once you start, you have the amount of energy fixed, into the linear mode, which increases as you press the foot pedal. And this, you can titrate the amount of energy you are using. So maybe you can just use the least energy that you need. And change from continuous mode to pulse mode. And by this way, again, you are decreasing the amount of energy. And the adjustment here is going to be taking an advantage of the off cycle of your phaco. And during the chopping, the most important thing in chopping is to create that purchase to hold that nucleus in place. So if you want to hold it, then you can use the pulse mode, you can hold, or the burst mode, you can hold it in place and then go back to position 2, which is only vacuum. Once you are holding it in place, then you can chop and crack that piece. Then you go back to press the foot pedal so you can emulsify and eat those pieces. Now, the importance here is you don't exert too much vacuum or too less vacuum. Too much vacuum will just eat up the piece sometimes without proper emulsification and may clog your system, and too low will not hold the piece in place. In quadrant removal, again, I use the linear pulse settings, and this will allow the nucleus to emulsify and the off time to help the aspiration to get the next piece into the tip of the needle of the phaco machine. So we're touched a bit of the basics of phaco-dynamics. Now, the first part, which is the ultrasound, we're going to talk now about the fluidics. The fluidics basically is a term used to describe the balance of fluid inflow and outflow. The main idea or the main concept behind it is to create a stable anterior chamber pressurized enough to help you do the procedure without damaging any structures like the cornea, iris, or lens. So we talk about the irrigation, inflow, the aspiration, vacuum, and we will talk a bit about the pump. The pumps, we have two pumps, the peristaltic pump, which is an example of a flow pump, meaningly that it allows for independent control of both the aspiration rate and the aspiration level. The other kind of pump is called the Venturi pump, and the Venturi pump is a vacuum pump. So this pump allows direct control of only the vacuum, and the flow levels are dependent upon the vacuum levels. The inflow, as its name means, it's the fluid that comes into the eye, which is BSS solution, through the needle tip. The approximate pressure is 11 millimeters pressure of mercury above ambient sphere is produced for every 15 centimeters of bottle height above the patient eye. So basically, if you're used to a pressure elevation of about 90 centimeters, you can calculate how that is going to affect the pressure of the eye. For example, in myopic patients, I slightly decrease the bottle of the bottle because it creates a lot of pressure on those high myopic eyes and a lot of pain. And so on. So you have to remember that you have a bottle that you can adjust the height in order to help in your surgery. The outflow is the opposite, the fluid that leaves the eye, and it can be left in two ways, either through the aspiration that works before the tip is blocked. It is reported in cubic centimeter per minute, and it is determined by the speed of the pump in peristaltic pump, for example. And this aspiration flow rate is basically how quick the pieces are attracted to your tip. So if you have a higher aspiration, these pieces are more attracted to your tip. While if we're talking about vacuum, or we can call it the holding power, which is a pressure of difference between the 2 points, this negative pressure, which is measured in millimeter mercury, determines once the occlusion of the tip happens, the nuclear material will be held up to it. So the vacuum is how tight the nucleus is held when the tip is occluded. The balance between those two, the inflow and outflow, is called the fluid balance. The bottle height is placed so the pressure is adequate, and so we have a stable anterior chamber. And the other term that you need to know is the followability, which is the combination of the forces attracting the segment and repelling it away from the tip. The imbalance, on the other hand, whether it is the eye is under-pressurized or over-pressurized, can be caused by many factors, but at the end, both of them have different complications and unwanted end results after your phacoemulsification. For example, iris trauma, corneal edema, zonular weakness, and so on. The surge is a term you will hear a lot, and it is basically due to something called tubing compliance. The additional source of vacuum builds up when the phaco-tip is occluded. If the phaco needle is occluded, the tubes collapse with the negative pressure, and once the occlusion breaks, everything comes outside from the eye, and it causes sudden expansion of the tubing, and hence everything is out and causes collapses of the anterior chamber and temporary shallowing. And of course, this is very dangerous, can cause posterior capsular rupture and cause corneal trauma. To reduce the surge, you select low levels of flow and vacuum. The rigid, non-compliant aspiration tubes can help in reducing surge. And another mechanism is called venting, which is implied in most of the phaco machines. So both safety and efficacy of the phacoemulsification surgery are directly related to the energy, the ultrasonic power, and the fluidics, and the proper setting and the use of the machine will improve the safety and efficacy of the surgery. Improper setting can create a dangerous situation. So always imagine it if you're having a very strong sports car, but if you don't know how to drive it, it's very dangerous. Thank you very much.